Great. Okay. So, so just a few of logistics. So now we have a WhatsApp group. I'll open it once a week at Mondays, I think they're out, right? And then it's open for all discussions. Otherwise, I highly prefer that you write me an email. It takes me about less than 1 day to respond. But sometimes the WhatsApp is not super convenient for me, so I really prefer the mail. And besides, I also want to start sending you emails to your real emails. I know that I already use the Moodle emails, but for some of you, these are this is a special program of Bar Ilan that you can send through the university things and so on. But I'm not sure if it's accurate, if the mailing list is accurate. So for this reason, I asked you to fill in the form of nice to meet you. And during the next week, I will say about it again. But if you didn't fill the form, so please fill it so I can start sending you emails instead of WhatsApp messages that we need to key in and so on, and then you just get lost, okay? Now about the recitations, since some of you talked with me and felt that there are some gaps in the level of the people of the course, so I decided to add 2 classes within each week. One of them is a mathematical class, will always occur on Sundays. The reason I do it on Sundays is that I want to do it before Izam, before the lectures. So when he talks, for example, next week, he will talk already about sampling and about delta functions and so on. So I already want to start talk with you about it at Sunday, okay? And this kind of reinforcement will be given in English because they are mainly, because most of the people that came to me came from the Erasmus, but anyhow, the course is in English, so it doesn't matter. Now, alongside, we have also another reinforcement at each Wednesday, right after the recitation. The recitation is mandatory. I'll tell you a clue. I don't care really if you come, and I don't care if you prefer to watch the videos or watch the videos from previous years. I really don't care how, if you come or not, but I highly recommend to come because then if you have questions, so we can talk about it face to face and not wait until, I don't know, until Santa Claus arrives or something like that. I have it for 3 years. Don't panic. The truth is that I want to see the people who joined us, so maybe I'll split it. And then, okay. And then I'll just put this here. And great. Okay, so what I wanted to say, yes, so I highly recommend to come to the recitations, reinforcement. I'll talk with Sophie and let her know if something is, I don't know, irrelevant for you. Yeah, best Sophie in the world.
No, because I don't know that, I am the
yes. I think that I need 2 representatives at least. One Israeli, that I can talk with you about how it is to study in English and if you have enough materials, and to send you personally some videos and so on, so they can help you. And someone for the whole course, which can also be Sophie, who is helping me with everything which is related to mathematics. Okay, so please, Israelis, let me know who is your representative. And I will talk day by day only with one representative. Otherwise, excuse me? Great. So Noah, you are the Israeli representative. The Hebrew representative will be more accurate. Great. Okay. So anyway, I sent you a self-learning recitation about probability and statistics, and I just want us to read this together and speak a bit about probably some new terms. I can say that I will say it also in the following recitation, but when I said that we need maybe a mathematical reinforcement, I really want you to understand that I don't want to teach you math, okay? Because I did my first degree in physics and math, and then I studied the mathematics, and most of them are irrelevant for the course. What we want to talk about it is the practical math. So whenever I explain something, I might explain a bit about the functions and so on and some of the math itself, but the main thing is more to understand how to use it. And most of this course is going to be very analytical, which means that you are going to write algorithms and you are going to solve problems by understanding the math behind them, but you don't really need to understand the very thorough math of stochastic processes and so on, okay? Don't worry, you don't need it. So the same about probability and statistics. So what do we need to know about this area? Some terms, and we need to understand what they mean. So I brought here a nice citation from a book that I really like, from Barrow. And in this book, he says something really nice. You really need to use statistics and probability in everything in science. You cannot unuse it, but you can do it by understanding it basically or clumsily, or you can use it skillfully. Okay, and in between, I want you to be at least at the basic level so that you can understand. And while you will go into your lab and then learn by touching the data with your hands, you will much more understand all the ideas that we are talking about, which are now a bit more vague, okay? But we need this just to a place to start. Okay, so when we use probability and statistics, when we want to use it, we need to use it on quantitative data. What does that mean, quantitative data? We have two kinds of data. We have qualitative and quantitative, right? Now, qualitative in Hebrew, איכותי, איכותני. This means that if we want to give it a number, we have to make a kind of a transformation. For example, if I want to say happy is 5 and sad is 0, this is like a kind of a transformation that I'm doing. This is not direct. Quantitative data, for example, is data that is that when we record the electrical potential of a membrane, this is a quantitative data. Okay. Now, in this course, we are going to use all the time discrete data, not continuous. What does that mean? The data itself of the membrane is continuous. If I have here a membrane and I record it by an electrode, right? So the membrane, if this is time and this is the voltage, the membrane can do things like this, go up and down and so on, right? But when I sample it, I have to sample it by digitizing it, which means that I'm not recording each one of the dots. I can record, for example, a dot here and a dot here. And this is discrete data. Or I can take an average here and another average here. But all of our data is discrete, right? So when I'm going to talk about probability and statistics, although I'm going to show you some of the functions which are continuous, we are going to talk about discrete data, okay? And this is the more important use of our fins. For example, I want to show you a nice fin. How do you make a derivative, a discrete data? Just to understand the idea.
Just measure the change in each one of the axes.
Great. Okay. So when we make a derivative of a continuous data, right? If we have, for example, the function, this is a continuous data, continuous function. And if I want...
Sorry, could you show the board?
Ah,
for
sorry,
the
sorry.
demo? Thank you so much.
I didn't even notice. Sorry. It's very good that you told me, because I tend to forget it. Ah, okay. It's really okay. The best is that I show it, because I always forget. Please let me know if I forget again. Okay, so if I make a derivative, then this equals to 2x. But how did I make the transition between this and this? So I have a function, and this function means that I take the differences between the two y's over a difference between two x's, and I look at the change when x1 is almost equal to x2, right? And this is how, this is like a kind of a nice idea, theory that you learned about in calculus, but then you have all these rules that you just memorize, and this is how you know the relation between the function and the derivative. Now, when we want to make a derivative of digitized data, we need to use it, but we cannot make this limit. So we can still subtract two samples, one from the other, while they're one after the other. So when I want to make a derivative, so I'll take the value here and the value here, and I'll subtract between them, and then I'll have the derivative, right? And this is commonly the function diff when you use Python or any other language. Okay, and this is what it does. It makes the differences between. Right. Okay, so this is, for example, about the differences. Great. So okay, so now for the statistics itself. So who would like to explain to us what is random variable?
The type of data that you are measuring.
The random variable? Okay, this is a new term, and this is irrelevant to the type of data that you're using, okay? So when we have probability, probability is a function that you take events or variables from one group, and you have a function of their probabilities, right? Now, there are a lot of things about this function. I don't know if you remember all of them. For example, this function has to be between 0 and 1, right? I don't know the word in it doesn't matter. I'm not sure about the word in Hebrew either. So, but all the values of this function here, of the probability, has to be between 0 and 1. Now, these types of random variables can be either from a continuous measure. For example, this is all the numbers of heights of people. What could be the number of heights of people? But let's, for adults only, and it could be between, let's say, 0.8 meter to, let's say, 2.5 meter, right? Okay, something like that. I kind of exaggerated. And then we know that most people are somewhere around 175, right? Right, so we can say, we can have like a kind of probability function that we have all the heights, and then we want to know what is the probability to be in between. So what is the probability to be at 0.8? Very low, right? Around, let's say, 1% of the population is 80 centimeters, midgets, and so on. Okay. I don't know if it is a PC word. I'm not fully sure about it. And how many are 2.5 meters? Also not very, some of the NBA players or something like that. Again, something like this, 0.01. And how many are 1.75? Let's say 68%, 50%, 60%, something like that. So around 0.6. And now I can have a function. I can also plot this function, which here I have the probability, and here I have the height. And in this one, so I know that in 0 I have nothing, and somewhere around 0.8 I have the beginning, and around 2.5 it ends, and it looks like this, right? The probability is the highest for 1.75 centimeters. Now, this is continuous, right? Because you can have every height in between 0.8 and 2.5. So this is not discrete yet. We have a function which relates between all the possible heights and all the possible probabilities, okay? Now, probability could also be something discrete. For example, how much money you have in your wallet. I don't mean about credit card. Let's talk only about coins, right? So you can have 1 coin, 2 coins, $1, $2, 200 shekels. I don't care, okay? But this is discrete. These are only specific possible numbers. You cannot have, for example, 3.1413 new Israeli shekels, right? You cannot have that. Maybe in your bank you can, but not in your wallet. So you have only specific possible values, and then you have a discrete function that relates between each of the values and the probability. And when we want to draw this kind of probability, we draw it like, let's see. So we draw it like a step function. So for example, if I want to look at bins of heights, all the theta between 170 and 175 and so on, this is our bins of the height itself. So we have a kind of a step function or a histogram of this probability function. Okay, great. So what is the random variable? This is the x-axis of the probability function. So a random variable can be anything. This is the cool thing about probability. You can have either a number, you can have an event, you can have a reaction. Everything can be a random variable over here. And you can relate everything into a probability measure. Okay? Now, some of the things that we know about random variables. So first of all the possible variables in a sample space, altogether their probability is 1, right? For example, if I toss a coin once, so I have either 3, how do you call it in English? Head and tail. Great, thanks. So it's a 0.5 probability for head and 0.5 probability for tail, and together they are 1. Okay, so this is what we see here. The sum of the probabilities is 1. Another thing that we talk about is the independency. So in probability, we have a quantitative measurement of independency. So we can look at the probabilities of two events. If two events are independent, which means, for example, if I toss a coin and then I toss it again, will it be affected by the previous toss? No, so it's independent. It is not affected by the previous one. So if the event is first toss and second toss, this means that the probability for both of them is the probability for the first one and the probability for the second one, right? And what happens if they are dependent? Do you remember? You need to subtract the intersection, exactly. So here we have, you don't need to know this for this intro. I have nothing here. So the full formula is P of A and B is the probability of A plus the probability of B minus the intersection between them. And if they are independent, then this equals 0. Right, okay. Is this familiar to all of you? Any questions so far? Because I have like a kind of a very long monologue. Okay, it's clear. Okay, so we have here a nice exercise to see that we understand. Do you want us to do it together or just go on? Okay, so we have, yeah.
I just have a in the solution.
Yeah,
Um,
there might be mistakes, by the way. Okay.
the last one apart. I don't know why it is not an independent.
Ah, it might be also. This is just an example.
Ah, okay, it's not the only
Yeah,
solution.
it's not the only answer. Do you want us to do it together? Maybe just no need, I think also. But what I do want you to look is, okay, let's just look at the first two and three lines, right? About how we calculate the probability. So what we do when we calculate the probability, we say how many cards do we have? We have 52 cards. And then we put it at the denominator, right? And then in the numerator, we put the value of the number of events that happens. For example, 5 of hearts, this happens only once in every deck, right? I will say it in Hebrew, כמה קלפים יש לנו שהם 5 לב? Only one. We have only one card, which is like this. So this is the reason why the probability is that we have one element. So the probability that you can choose this card is 1 over all possible cards, 52, right? Now, how many kings we have? 4, exactly. So how many kings can we see in the probability? So we have 4 elements, so it's 4 over 52, right? So please remember this, because I don't know why when we start to talk about spike counting, we always forget to divide it by the number of all possible spikes. And this is just about moving into probability. We don't want to talk only about the number of spikes, but also about the probability for a spike, right? Great. Zoom, are you okay? Do you have any questions?
Oh, good.
Great. Thanks. Okay. So I was a bit misleading, but I did it with a good purpose when I talked about the probability function, because when we talk about probability functions, we have two kinds of functions. The first one is the cumulative distribution function, and the second one is only the probability. Which one was this? The probability, how do you know? Yeah, exactly, because the cumulative looks different. Every time you see a cumulative one, it climbs into 1. It has to arrive to 1. I have it only in the end. I'll show it in a minute. Let's see. Okay, so here is, for example, the cumulative of a PDF function, right, of a Poisson distribution, and you can see that it reaches towards 1. And this means that it's a CDF and not a PDF. So do we use CDF? Yes, we do use it. You will see it when we talk a bit about a Poisson neuron, which is the most relevant model of how a neuron works. But commonly when we talk about probability, we talk about PDF. So let's just see that we understand what is written here, the mathematical gibberish. So first of all, CDF is an integral, which means that when we are looking at discrete functions, it is the sum, right? Integral becomes sum. Derivative becomes differences. So it's the sum of all probabilities so far for events from -infinity to this specific event. Now, sum of its features, when it's at x equal -infinity, it's 0. Its top is at 1, right? And if you have two variables, 1 minute, that you have x1 is smaller than x2, then the CDF of x1 is smaller than x2. It has to be a climbing function. Yes, sir.
Yeah, I was wondering what means the x compared to the small x here? Yes, and
Yes.
it's written fx of x, and on the right it's also an f of x.
Yes, so this is a group. This is a group. The group of all possible random variables which are smaller than a specific one.
So on the left, it's discrete, how we write it for discrete, and on the right, it's how we write it for
No, this is the... No, this is true for both of them. But this is how the function looks like, right? This is a kind of an explanation that is... Yes, yes, of course.
I don't understand why it is here and not here.
This x here, you mean?
Yeah.
I could write it also here.
Ah, okay, okay.
Great, okay.
It's the same.
Yeah. Now, what we see here that if we have group of variables which are greater than a specific value, here it's only smaller or equal. Here it's greater, then it's 1 minus the CDF of that variable, right? I don't remember the word in English that you say that it's, how do you call it? Mashlim? I don't remember. Okay, it doesn't matter, but it's 1 minus the CDF. Okay, now if you have a value in between two possible other values, so it's the bigger minus the smaller, great. And then we have the same thing about PDF, just note that PDF is the derivative of the cumulative. Okay, so please note that when we're doing a PDF for discrete values, so we have a step function, and also the derivative should also be a step function, right? Okay, and this is about the same. Great, let's go on. Right. Any questions so far? This is very, very, very dry math.
No, it's just about this one. wondering if maybe it's
Yeah, you can add here the equal. Yes,
yeah,
yes.
because for continuous it doesn't change a lot, but for discrete it can change a lot, right?
Yeah, because of the steps. So if you do it only smaller, yeah, you're right. Okay. So, and also write me so I can add it to the notes. Great. Now, these are three terms that not all of the students are fully acquainted with. And it's average, variance, and standard deviation. And you probably heard about it a lot also in the news. So please tell me what each one of them means. What is an average? Why do we care? Okay, let's ask another nice question. I heard it in a very nice lecture. Why do we care about the average?
So we cannot consider all the
Great. Okay, so we care about average because sometimes it's very helpful to use the average. For example, look at the chairs that you're sitting in. These chairs were designed by the average height of the population. Did you ever think about it? Okay, so the chair height is based on the fact that the person with the height of 175 is sitting on it, and then it's relevant for him. Think about another possibility that maybe we could have a different chair for each height. Would it be easier? What are the costs of such a factory, right? Now let's ask, for example, that you can do something like this. You are now you now want to engineer a new bank, and in this bank, the size of the bill is the size of the money in the bill. How would look such an average? Okay, let's say, for example, that the storage that you have for each person with a bill is the size of that bill. How would you engineer such a bank? Tell me something about the wealth across the globe. I will ask it again in Hebrew. I ask it and I like the fact that I see you thinking. Okay, you don't need to know the answer. It's a thinking question. So I ask it now again in Hebrew and then you have some more time to think. אם הייתם מתכננים עכשיו בנק שבו הגודל של כל חשבון או הסטורג' של כל חשבון הוא ככמות הכסף שיש בו, איך הייתם מתכננים? Let's say that let's say those are safes. Yes. For each person, he has a safe, and the size of the safe is as big as the money that he has. So what is so problematic about this question? Yes, but height is also personal. So why can you design a chair and not design a safe?
Because I think the difference is much bigger.
Great.
4%.
Great. So when we look at the function of probability of wealth around the world, so we see a very different type of probability. It does not look like this, which is a normal distribution. We have a probability that looks like this. Most of the people don't have a lot of money, and some very few of the people have a lot of money, right? And then if you want to have a safe, which is the average money, what will be the size of the safe? It will be around here, right? Because most people have very few money. But then you have problem about the people with a lot of money, that your safe could not be suited for them. Okay, so I wanted to show you this because the nice thing about it is that you understand, you kind of understand an average. You understand it that there is an equation and you need to take a sum and then divide it by the number of events that you're taking and so on. But then you need to ask of you always need to ask yourself if the average means anything. And sometimes it doesn't. For example, the average size of a safe in a bank means nothing about the probability, the distribution of wealth around the globe. Okay, so how would you again engineer such a bank? Excuse me?
Oh, I feel that like maybe, I mean, instead of using average, we use like other tendency like mode or median, because like, for example, like it's not normally distributed, but like majority would be on this side because like most of the people are not rich, you know? So like it might be more efficient to use like model like to see the like how many like.
Okay, so if I understood you right, you're offering maybe to give more than one safe for someone who is richer, right? If I understand, okay. So I also thought about it that you can just build different kinds of safes, right? You can have small safes, which are for people with less money, and then you can have big safes, and you can allow some of the people have more than one safe, right? And this is how you can do it. But you cannot design the average safe, a safe for all of them, one safe to rule them all. Okay? Okay, so this is about the average. So we have here the formula of the average. And then we have another very important thing, which is the expectation, right? Now, please note, this is a question that Izar really likes, and I don't want you to confuse. Expectation and average are almost the same. Okay, what is the difference? Average looks only at the events, only at the numbers, and then it divides to the number of events. An expectation is the event and its probability, right? In what cases both things are the same? Normal, uniform, right? But and by the way, I think that in all cases these are the same. But just please note that when Izar asks you a very stupid question about 20% of the class students got 90 and 80 got 100, and then he asks you what is the average or what is the expectation, so you need to use this formula, right? So for example, in the very simple question that I asked you, 20% of the students got 90 and 180 got 100. So what is the average? What is the expectation? So yeah, 90 times 0.2, right? Because it's probability, plus 100 times 0.8. Okay? Right. So this is the expectation, and it's about the same as the average. And then we have the variance. What does the variance mean? Yes.
The variance show how much each individual is different from the average.
Yes, exactly.
If the variance is large, it means that people are really different, and if the average, the variance is small, it means that they are all the same.
Great answer. And then please note that we need to look again at the distributions that we're looking at, because talking about variance in normal distributions can have any effect. Yet when you talk about variance in for example, exponential distribution or Poissonian, no, Poissonian is okay, but exponential distribution, it might not be relevant, right? Because over here, the variance for this type of measurements is much smaller than the variance here. Great. And then we have the standard deviation, which is just the root of the variance, okay? Just the commonly used, right? Okay, great. And then you have this self-learning exercise. So you have here the function. This is a PDF, and then you're asked about I don't know, using a few possible x's. And I feel that you can deal with it, right? And if someone doesn't, please write me. Great. We're about to finish. Do you need any break? Are you okay? Great.
One quick question for these are courses and exams. We need to be able to do derivative integral and stuff like this by hand. We have to be able to do it fast.
At some level, yes, yes, yes. In some cases, you're asked to solve analytically some things, okay? And mainly at the, I don't know how it will be this year, but in previous years, we had also, instead of a final exam, we had quizzes along the course. And I believe that also in this course, it will be 3 or 4 quizzes. And then it's commonly, it is very common that Izhar is doing a quiz, for example, for 4 weeks or something like that. And then at least one of them is by handwriting. So yes, you need to solve analytically. Yeah, I think yes. Yes, probably. Yes, yeah, it's okay. Okay, so stay tuned because we are about to finish. We are now talking about distributions which are for 2 variables, right? Because so far we talked only, for example, of height of one person. What is the probability? But we might have more than one distribution. For example, we are interested in the question if there is any relation between height and age. Is there any relation? What do you say? Yes, exactly. So now we want to quantify. So how can we do it? So the age is one type of a probability function and the height is another. So now we want to check 2 possible relationships between them. So the first one is called covariance. And as you hear it, it's the variance of the jointed distribution. So this measurement is kind of, look, it's the expectations of both of them together minus the multiplication of each of the expectations, right? So what does that mean, the covariance? So the only thing that we're interested in covariance if it's hi. Welcome. So we're interested in the question if it's positive or negative or 0, right? So for this reason, we have this Pearson correlation, and Pearson correlation is a kind of a normalizing way to use the covariance. And then if you have the Pearson, it's the covariance, and you divide it by the standard deviations of each one of the distributions, right? And again, what does that mean, the Pearson correlation? So now instead of positive and negative, you have possible values between -1 and +1, right? Where 0 means that the 2 distributions are not correlated and the relationship between them is random. For example, which two distributions are random? Give us an example. The color of the, yeah, the color of the eye and the color of the hair. They are not, they shouldn't be matched by each one. Or the height and the money in the bank, okay? They are not correlated. Yeah, I'm a very high, yeah, I wish that I was, that there was any relationship, but maybe the height and the happiness, or something like romantic like that. So that means that they are uncorrelated. And then let's take something that is correlated. When it's around one, they are in full correspondence, okay? So that means, for example, as we said, the age and the height, they should be very highly correlated between each other, right? And we will talk a lot about this thing called correlation and about information, the information that if you know something about the height of someone, for example, if I know that someone is 80 centimeters high, so probably I know also his age, right? Because 80 centimeters high is probably someone whose age is 1 or 2 or something like that, right? But there are some people that are 30 years old, right? As we talked about them. So there is some relation, there is some information that both of these things, when you know one, you can say something about the other one. And this is something that we'll talk about more when we talk about information theory. And we will use all these measurements to fully measure the relationship in the information between them. Okay, and then we have a Pearson correlation is -1. And when this is -1, it means that both of them are opposite to each other. Okay, so for example, the grade of your exam and your sadness after you got, right? They are fully opposite to one or another. And I really hope that you are somewhere around the average for each one. No, I mean like not for the grades, right? But at least for the sadness. Don't be that sad. If you would only know what were my grades at my first degree. Okay, so what did I want to say more? Okay, so we have Pearson correlation, but please note that when we're talking about measurements, we don't only use the Pearson, we also use the p-value of the relation between them, because we want to know how significant is the relationship itself. And this is the kind of thing that we won't talk about too much in the course, because we're not talking about significance. But please keep it in mind that it's always in the back of your mind, that it's always there.
Other correlation experiments.
No, we are not. I don't know even the reason that I talk about the Pearson is only in order to be able to compare this, which is very straightforward, to, for example, mutual information, which is another measurement that we will learn in the course. Right. Okay, so you have here two variables. Each one of them is another is in a different axis, and then you need to determine if they have strong correspondence or not. And you can just by looking at them say, right? So for example, here, is this strong or not? Strong and positive, right? And you can see that they are almost have a linear relationship. So you know a lot from one about the other. And here they are opposite. They are uncorrelated, but they still have a relationship between them, okay? Great. So I had here like a nice exercise that, because we are in signal and data analysis, so think about two signals which are highly correlated but different. So we talked about possible distributions, but you can also think about signals. Okay, and this is the last subject. So distributions. Okay, are you okay? Can you handle it? Great. Okay, so distributions. So I really want you to know what does that mean. Distributions is like a kind of a pattern of a probability function. So for example, we have a uniform distribution. What does that mean? A flat function, great. So it looks like this. But what does that mean, a uniform distribution? Exactly, exactly. So for every possible event or random variable, the probabilities are equal, right? And here it is for a continuous case, and for a uniform distribution, it's just the number of events, and it's 1 over the number of events. Okay, so when do we use this? Oh, it's here. If we have k events, so it's 1 over k. So when are we using this kind of distribution? So we have, yeah, a 6-sided die and most of the events which are independent of each other. So we commonly use uniform distribution. Okay, and then we have the binomial distribution. And we commonly use it to describe the number of successes. For example, if someone is in the NBA, so we can ask ourselves, what is the number of successes of putting the ball in the basket and in a set of trials, right? So please think about the kind of this small quiz that I sent you. And please note that in one of the questions, it's not fully clear, but there is a binomial distribution. Think about the question, and the question looks like one thing, and then if you think about it, it's more a question about success within a given set of trials. Okay, and then we have for this
What is n in binomial?
what is n here? The number of possibilities, all possibilities. Now, for example, number of throws to the basket, and x is the success. And I don't know if you know this this form. This is a form that you can put also in your calculator. That someone doesn't know, what does that mean? It's the Pascal binomial and so on, and there is a. I'll write here. If someone needs the equation, because maybe for some of you it helps him to understand it better. So n over k is n, how do you call this sign? Factory, right. N factory over n minus, no, it's not over, right? I forgot it.
The n factorial over n minus x.
No, it's not like this. N minus k. It's over n minus k?
Yeah.
And that's it?
And then k factorial as well.
This is what I remember. So it's something like this, right? Oops. So it was okay at the beginning?
On the top, you have to remove
n factorial למעלה וכל השאר למטה.
Okay, right. Oops. Okay. So you see, it means nothing. So, but it says, but just remember, it's the number of successes from a given possible trials. But we will use it, okay? It is a very important equation to remember, because when we talk how you generate a Poissonian neuron, we use this, okay? And we have a good reason to use it. We'll talk about it. So please remember the binomial distribution. Another distribution is the exponential distribution, and we use it in neuroscience to describe the distribution of intervals between spikes. Okay, so this means that a neuron is not fully random, right? It has like its own kind of organization within the number of possible intervals of these neurons. And then the probability for each interval is driven from an exponential distribution. And the exponential distribution is also the distribution of wealth that we talked about. Right. So this is it, and please remember this drawing. It is helpful, and we will use it a lot. Great.
Is the first one is the little f, it's the equation of PDF, and the
Yes.
second one is the
The
of
CDF. It's always like this, that the small f is the PDF and the big F is the CDF. Right. Okay, and the queen of the distribution is the normal distribution. And why do we care so much about normal distribution? Okay, so we have the central limit theorem. This is, as I said, this is the kind of thing that you don't need to understand the proof from math, but you need to know the name. So the central limit theory means that all distributions, or most of the distributions, that when they have a lot of samples, or when n is reaching infinity, they start to act like normal distribution. And this is the reason why we have so many things about variance and standard deviation and average, because all of them are relevant when you talk about normal distribution. But they're irrelevant when you talk about other distributions, which are only now gaining their own glory. For example, the exponential one. Right? Okay. So do you want to ask anything, Tali?
I remember something about
Yeah, it's kind of the magic number, but it doesn't matter. We just say that when you have a lot of samples, so it becomes more relevant. And of course, binomial distribution, for example, becomes very close to a normal distribution. Okay, now what are the things that we see here? Because I really, really wanted to fully understand it. So what we have here is the mu is the average. And the memutza is also the most expected value. This is another word that we didn't talk about, but this is the highest probability one in normal distribution. So it will always be in the middle, right, of the distribution. And what is this sigma that we see here? The standard deviation. And what does that mean? How wide the distribution is. So for example, we have here a sigma of a variance of 0.2, and you can see that it's much more narrower than a variance of 1, which is the red. And also the yellow is 5, and then you can see, for example, the mu equals -2, and then it moves to its left. Right. Okay.
What was the name of the numerator?
Of the numerator, the standard deviation or the variance? The sigma. This is the letter sigma in Greek.
No, in the numerator of the exponential.
Here?
It's
It is. This mu. Sorry, mu is the expectation, the average. Yes. Great. Now, when we talk about normal distribution, we're going to talk a bit. You probably have you seen the shirt of Osnat with the normalizitis and so on, right? So there is something that we will talk a bit about it, and this is called moments. So I don't know if you noticed. I'll go again. here. Right, so please tell me there is a relation between the expectation and the variance. What is the relation between them? Please look at these two formulas, right?
Variance expectation of square value minus the expectation square.
Yeah, okay. So you can say that, but you said two very important things. So first of all, you said expectation. And the second thing that you said is that we have this square here. So we can talk about the relation between expectation and variance as a relation, as a kind of global relation between moments, where the expectation is the moment of 1, and the variance is the moment of 2. And then we have 2 more possible moments, the third moment and the fourth moment, where you can see that each moment is the expectation of the value with its with its order. Thanks. Okay, so if the order is 3, then it's third moment, right? This is just another way to write them, and you don't need to really calculate them, as far as I know. You just need to understand what do they mean. Okay, so we have the skewness and the kurtosis. And you can see here the skewness is the moment of is the third moment, and the fourth is kurtosis. Let's talk first about the skewness. The skewness says what is the relation between the sides of the distribution, right? If you have a positively skewed distribution, so you have a kind of a left side preferability, right? And you have, if you have a negative one, then you have a right side preferability. And you see it, right? And then you can look at the kurtosis. The kurtosis is, please note not to get confused with the variance, because many of the students don't understand the difference between kurtosis and the variance. So here we don't see differences in variance. What we see is kind of how flat it is in the upper part of the distribution. So if you have something which is mesocortic, it looks like a normal distribution. But if it's more peaked, right? So you can see here the variance is the same, but it's more peaked, then the kurtosis is bigger than 3. And if it's more flat, then it's no, this is the one with no, this is smaller and this is bigger, right? So the more peaked is the leptocortic, and the more flat is the platycortic. Like platypus, if you know, the animal from Australia.
Are they all normal though? Because
Yes.
if the variation doesn't change and the average is the same, how do you distinguish them kind of in the language of normal distribution?
All of them are normal distribution, and the differences are in the higher moments. Now, how do you add them? So what we see here, when we saw the normal distribution over here, so you can just multiply it by something, and you have it in Wikipedia. It's really easy to get it. And then you can add in also the kurtosis or the skewness and so on. And it is really strange to say that this is very, very useful. For example, I did a model of normal distributions because everything in neuroscience is normal. Not the clinical population, but all the distributions in neuroscience are typically normal. And then sometimes you do want to add skewness or kurtosis or something like that. And then you have, it's very easy to add it from Wikipedia. Okay, and that's it. You made it. I know it was very, very dry. I really try to add some picanteria. And I hope that the next class will be much better, and it will be Wednesday. And again, for the Israelis, please note that after the recitation on Wednesday, we have the Hebrew reinforcement to answer questions in Hebrew, only in Hebrew. Okay? So I also plan to, please tell me if you want to have another lesson at Sunday. And at Sunday, I want to talk about specific mathematical issues that are in relation to the things that you're going to study this week with Izam. So let me know if you're interested. Yes, Sophie will update you. Okay. So Sophie and Noah, you are the representative, and great. Thank you for Zooming with us.
Thank you so much.
You're welcome.
Can I ask you a question about